Okay, so let's start by defining them. So neural networks have layers. They have so here's the input layer, which we're gonna number it with a 0, and the output layer we're gonna number it with an L+1. So there's gonna be L hidden layers. So 1, 2, ... up to L, and every layer has some kind of width. So the input and the output are fixed. They are n in and n out. And we might take n out to be 1. It doesn't really matter. But they have the input and the output dimensions. And we have these hidden layer dimensions, n1, n2, all the way up to nl. So these blobs are supposed to represent sort of collections of neurons of the number that you have. So that's what these little blobs represent. And the first and last ones are fixed, so we can these ones are fixed. But the intermediate ones, we can change their width as we want. And what we do is we define a function by starting at the input and just applying matrix multiplication and an entry-wise nonlinearity to go from layer to layer. So written out, what is that? That's this definition. So every layer has a function. So there's f1 of x theta, f2 of x theta is the second function, and so on. And that tells you the output of each layer. And they're defined recursively. So f2 is defined in terms of f1, f3 is defined in terms of f2, and so on. So what's the formula? F1 of x theta, it's you take the input and you just apply matrix multiplication to it. So I'm going to say W1 are the weights of the first layer, and we do W1x, and we'll have some biases. Bias 1, so this is an n1 by 1 bias vector. The weight matrix, the first weight matrix is an n1 by n in matrix. X in is an n in by 1 vector is the input. And we're going to normalize things just like we did in the previous videos. So the first thing, I'm going to divide by the square root of n1. And that's exactly because that's the right thing to divide by, so that in the limit that n1 gets very large, this whole thing settles down to something non-trivial. Okay, and I'm also going to allow two parameters here, sigma w and sigma b. These are sigma w, sigma b are the standard deviations, so let's write SD, of the weights and biases. So the parameters themselves are weights and biases. So this weight matrix and these bias vectors, and they're always going to be initialized to be mean 0 and variance 1. And then I'm going to multiply them by these things if I want to get some kind of non-trivial standard deviation. And that just makes sure that the gradient matches up with the variance. Okay, so that's what we're doing. That's the first layer. So far, that's exactly what we've been doing before in the feature regression model. So so far, nothing new. So F1 you can think of as a feature regression model where the features are nothing. The features are just the NMD. But now it starts to get interesting. So let's scroll down a little bit. So F2 is going to be defined in terms of F1. But sometimes what people do is they first they define a post-activation function, h. So h is like f, but you apply a nonlinearity entry-wise. So phi of f1 x theta. So that's applied entry-wise. And phi is some nonlinear function. Some nonlinear activation function. Okay. Okay, and then once you have the outputs, you just do the same thing again. So in general, f2 of x theta is going to be the same thing, sigma w over the square root of n l w l h l minus 1 of x theta plus sigma b times b l. Okay, let me do it like this. Let's make this. Let's just define it in general for the lth layer. So the lth layer is defined in terms of the L minus 1th layer, and HL is defined in terms of FL. So there you go. If you apply this recursively for all the different values of L, every time you do a new layer, your parameters get increased. So instead of being just W1 and B1, now you have WL and BL for all values of L. For L equals 1 to L. And finally, the output of the layer is just what happens at layer L plus 1. So the output of the layer is f of x theta is by definition just f of L plus 1 of x theta. So that's all it is. That's the neural network. So you've definitely seen that before. So it is a bit like the feature regression model, except more complicated. And the point is that even though it's more complicated, it's going to behave like the feature regression model. So